Okay, so this is a video for the third section on this handout number 2 for volume of revolution. And if you look at the third section, you may have noticed that we're not rotating around the x-axis or the y-axis anymore. So the first problem I'm going to do here is problem 14. So what we've got here is the curve y equals a half x cubed, the line, horizontal line y equals 4, and the vertical line x equals 0. So let's draw that and see what it looks like, and then we'll talk about what's going to happen when we rotate this around the line y equals 4. Okay, so here's the graph. So the y equals a half x cubed is going to look just like y equals x cubed, except that all the y values are going to be cut in half. And again, use your graphing calculator to take a look at this, but it's going to look something kind of like that. Okay? Let's see. The line y equals, well, let me label this. Y equals a half x cubed. And then the line y equals 4 is going to come in right about here, and then x equals 0 is the y-axis right there. So again, here's the area that we're working with. That's the spot that's going to get rotated. Okay? Now let me erase that so that we don't clutter up our drawing. Now, here's the trick. Now we want to rotate this around the line y equals 4. So again, just like I've been doing when we rotate it around one of the axes, we make a little mirror image on the other side of our axis of rotation. Looks something like that. And this is another thing that I've been talking about, is whether or not the area that we're rotating is flush up against our axis of rotation. In this case it is, okay? And so as a result, what we're going to get is a disk. Okay, there's the thickness of our disk. And again, that thickness is along the x-axis, and this is a dx problem, so we're going to be integrating with respect to x. What does this thing look like? You know, it kind of looks like this, right? Something along those lines. Okay, so now we know we're working with a disk problem here, okay? And so let's talk about our formula for the disk is going to be integral pi r squared dx. Okay? Now the key here is identifying the radius, because here is the radius right there. That's our r. Now, down here, when we were doing those other problems, this is where the radius typically was. It was the function value. This is the y value right here. This is y, which is 1/2 x cubed. That's that distance right there. There's the x, there's the y, there's the coordinate. So that's what's happening here, but notice that that's not the radius for our disk. Okay? So how do we get the radius for the disk? Well, we know that this little piece right here is a half x cubed. This whole piece right here is 4, because this is the line y equals 4. So our radius, let's see here, let's put it up here. The r is going to be the 4 minus the function value. 4 minus a half x cubed. Okay, so that's the first step in doing these, is if you're not rotating around the x or y axis frequently, you'll have to play around to figure out what that radius is going to be. Okay, let's see here. So now we want to set up our integral. We're integrating with respect to x. So let's see, this point right here where y is equal to 4, that means x cubed would be 8, which means that x would be equal to 2. And so those are our limits of integration are going to be from x equals 0 to x equals 2. And then our radius, like I said, is 4 minus a half x cubed all squared. So there's our integral. So let's do some algebra to it. 0 to 2, this will be 16 minus 2 and minus 2, so minus 4x cubed, and then plus a fourth x to the sixth. All right, so now we've got the algebra set up. Let's do our calculus. Do the integration. This will be 16x minus x to the fourth. And then let's see, this will be a fourth times x to the seventh over 7. So that's going to be x to the seventh over 28. From 0 to 2. So that's 32 minus 16 plus 128 over 28. And then minus 0 if we plug that 0 in there. So let's see what this comes out to here. 32 minus 16 plus 128 divided by 28. And so this should be 144 pi over 7, or some form of that answer, as I talked about in the previous videos. Okay, so there's the first example of a problem where we're rotating around something other than the x-axis or the y-axis. Now notice in this case we were integrating with respect to x. We wanted our function of x in terms of x. And one way you can see that is that our axis of rotation, even though it wasn't the x-axis, it is parallel to the x-axis. Also, our thickness is a delta x along the x-axis. So those are things to look for that can tell you whether or not you're going to be working with the function of x or whether you're going to be working with the function of y, which I think we'll see in problem 16. Yeah. Okay, so let's look at problem 16. Okay, so problem 16, we've got y equals x, y equals 0, y equals 4, and x equals 5, and then we're going to rotate around that line, that vertical line, x equals 5. Okay, so let's make a sketch for this and see what's going on here. Well, y equals x is a pretty straightforward function. That just comes through and cuts the first and third quadrants in half. Okay, y equals 0, well that's down here. That's the x-axis, all right. Y equals 4, well that's up here. Here's y equals 4 again. And of course, since this is the line y equals x, that's the point 4, 4. And then the other line that's going to define our area is going to be the line x equals 5. And so that's right here. So this is the area that we're going to rotate. Okay? Don't get confused by this spot over here. That's not the area that's getting rotated. Okay, so now we've identified what's going to be rotated. We're going to rotate around this line y equals 5. So it's going to rotate like this. So we want to put our mirror image on the other side of that line. There it is. Let me erase our slash marks here. Okay. And so our cross section is going to be right here. There's our thickness, and notice that our thickness is in the y direction. It's along the y-axis. So this is going to be a dy problem. We want these to be functions of y. All right. Let's see. What is this thing going to look like? It's going to look probably something like this. Okay. All right. Now let's identify our r. The only thing that's going to be different here, this is a dy. Okay, and again, all of those hints for why is this a dy? Why are we going to want functions of y when we're doing this? That thickness is along the y-axis, and notice that our axis of rotation is parallel to the y-axis. So that tells us that this is a dy problem. Okay, now we have to identify that radius right there. Let's see, let's put it somewhere where I've got lots of room. So there's our r. And again, this piece right here, this is the x value, which in our case is equal to y. Okay? So that's the function of y that we're interested in. And let's see here. So how are we going to identify this r? Well, let's see. This piece is y. This piece right here is 5. Okay? This is 5. This is y. This is 5 minus y. That's our radius. 5 minus y. Okay? So, now that we've identified our radius, this is a disk problem, so we're all set up to integrate. So this is going to be pi. Let's see, what are our limits of integration? Well, we're integrating with respect to y, so we're starting at 0, and we're going up to 4. Our radius is 5 minus y, all squared, dy. So let's do our algebra. 25 minus 10y plus y squared. And then when we integrate that, let's see, we'll get 25y minus 5y squared plus y cubed over 3. And we're going from 0 up to 4. So let's see what we get out of this here. That'll be 100 minus 5 times 16, so that's 80. And then 64 over 3, and then we'll get a 0 when we plug that 0 in there. So let's see what we get here. So that's going to be 20 plus 64 over 3, and so that's 124 pi over 3. Okay, so that's problem 16. Now we've got one more to look at. So let's talk about problem 18. And we are going to have a follow-up assignment for this, okay? So this is just an introduction to this concept of rotating around lines that are not the x or y axis. So this is going to be the last assignment for week 1. I'll get a video up. The first video for week 2 will be a follow-up assignment to this right here, okay? So let's look at one more example. Okay, problem 18. X equals y squared, x equals 4, and we want to go about the line x equals 5. So the fact that this is written as a function of y, right, it's written in the form x equals, so that's a hint that we may be integrating with respect to y again. All right? And again, notice that our axis of rotation is parallel to the y-axis. So let's draw this and see what it looks like. Here's our y-axis. So this function, x equals y squared, is a parabola on its side. Kind of looks something like that. Okay? Let's see. X equals 4 is, let's say, right about here. And this is the point 4, negative 2, and this is the point 4, positive 2. Now our axis of rotation is 1 unit over. It's this vertical line, x equals 5. Okay, so if we want to see what this thing is going to look like, we want to put a mirror image of our curve over here on the other side. Okay. Let's see here. Now, Where's the area that we want to rotate? I should have done that a minute ago, but here it is right here. This is the area that's defined by x equals y squared and x equals 4. It encloses this little section right here. So this is the section that's going to get rotated around that x equals 5 line. We're going to get something that kind of looks like this, right, with this hole in the middle of it. And where this thing is kind of like that. Okay, so that's what we're working with. Let's see here. All right, let's erase my hash marks. Now, the other thing that I want to mention about this problem is notice that the area that we're rotating is not flush up against the axis of rotation. That's what creates that hole in the middle of the object that I just drew, and that's what's going to make this a washer problem, okay? Our cross section here is going to have, we're going to have a little piece in there, and then we're going to have a bigger piece out here. And there's the thickness for the little piece, and there's the thickness for the big piece. Okay, so this is a washer problem, which means that we need the washer formula, which is r squared minus little r squared, and this is a dy problem. All right, so now we need to identify these two radii. Here's the little r right here, and then our big R is going to get extended to there. Let's see, where can we put it over here? Now remember that this piece right here, this is x, which is defined as being y squared. Okay, so this little r right here, notice that it doesn't change, right? You've got these two vertical lines here. Little r is always equal to 1. Doesn't change. The big R, though, again, this whole section right here, from here to here, is 5. This little piece right here is y squared, and so our big R is 5 minus y squared. All right, so now we're all set to go here. We're going to integrate pi, integral from, now, again, we're integrating with respect to y. Down here, y is negative 2. Up here, y is positive 2. So those are our limits of integration. We're integrating from negative 2 to positive 2. Our big R is 5 minus y squared, all squared. And our little r is just positive 1. Okay, so there's the setup. Let's do our algebra. Let's see, so this will be pi 25 minus 10y squared plus y to the 4th, and then minus 1. So I'll just make this a 24, okay? I'll clean this up a little bit. Okay, so there we go. Let's do the integral. This will be 24y 10/3 y cubed, oops, that's supposed to be minus 10/3 y cubed, and then plus y to the 5th over 5, and we're integrating from negative 2 to positive 2. So, to evaluate this, this will be 48 minus 80 over 3 plus 32 over 5. And then don't forget, we've got to plug that negative 2 in there as well. This will be minus 48, positive 80 over 3, and negative 32 over 5. But this minus sign is going to change all of these signs. And that's just going to double what we got in the first place. And so this is going to be 96, 160 over 3, and 64 over 5. And you can see that in some of these problems. If the two sections are symmetrical like that, you'll often get that scenario. Okay, so let's see here. 96 minus 160 over 3 plus 64 over 5. 832 pi over 15. Okay, well, like I said, these problems are a little bit tricky, and that's why I like to introduce them after we've looked at the regular disc and washer problems. And also, like I said, this is just an introduction. We'll follow this up next week with another handout that goes over these problems. And let me know if you have any questions. Thanks.